There's more ASFurther maths, and we're on complex numbers, and we're looking at the mod arg form of a complex number. Here's what you know so far. If you have a complex number z equals x plus iy, we can represent that in the Argand diagram as this distance here, this distance here, this is your x, and this is your y. You write the principal argument of the complex number as arg z, and that's your theta there. The principal argument then is between minus pi and pi, going this way here. Suppose the complex number x plus iy is represented in an Argand diagram by the vector OA, and B is the foot of the perpendicular from A, so it's bringing it down then from A to the x-axis. If we have OB, which is x, and BA, which is y, then OA is the vector then which takes you from O to A, which is the same as the modulus then of z, which we're going to call R. That's our modulus. The angle BOA is theta, and OB over OA is cos theta. Because if we were theta here, that's our adjacent, so OB over the hypotenuse, we have that. That means OB over R is cos theta OB, and is R cos theta. Similarly then, AB over OA is sine theta. I'll keep the wee diagram just above here so we can see where we're hopefully working for. And that means that AB, so that distance there, is the same then as R sine theta, with that distance obviously being R. So another way then of writing our complex number is z equals R cos theta plus I sine theta, because that's the x bit and fairly just kind of multiplies it through. This is called the modulus argument form of a complex number. So this is kind of a new form, so we kind of have a couple of different ways of writing it, and this is now a new form, and so it can be written kind of modulus argument form. So if you know the modulus, which is R, and we know the argument, sorry, you can't even see this, apologies, and you know the argument, which is theta. If you know modulus, which is R, and the argument, which is theta, then you can write it in this form here. This is called the mod arg form of a complex number. Multiplying and dividing two complex numbers then in mod arg form. We're going to skip through this nice and quickly, but if you have one complex number, looks like this, another complex number looks like this. If you want to multiply them, whenever you multiply them, you multiply their moduli and you add their arguments. So it ends up then looking like that. You can see it, the picture then, the Argand diagram. We'll not spend too much time on that, but that's generally how that bit works out. Here's the theory behind it, and you can see I've written in kind of big bold writing. So when you multiply two complex numbers, you multiply their moduli and you add their arguments. You can probably work out then what happens whenever you divide two complex numbers. If you have your complex numbers here, again, R1 cos theta 1 plus I sine theta 1, and Z2 is R2 cos theta 2 plus I sine theta 2. You divide their moduli and you subtract their arguments, again in bold. So when you divide two complex numbers, you divide their moduli and you subtract their arguments. Couple of wee bits and pieces about this then before we run on and try a wee example. Please note the following. The modulus of Z1, Z2 is the same as the modulus of Z1 multiplied by the modulus of Z2. Again, the same for dividing. Argument of Z1, Z2, of course, you add the two arguments. And Z1 over Z2, you subtract the two arguments. In the case of the last two results, you may need to add or subtract 2 pi in order to get it in between minus pi and pi, but I think that hopefully makes sense. That is so you still have the principal argument once you've added or subtracted. I think we know that. Example 1 then, given that Z1 is this and Z2 is this, find Z1, Z2 in the form A plus IB. So I think we eventually then kind of need to change it around. So we're asked to find Z1, Z2. So what is our rule? Z1, Z2. We multiply our moduli and then we add our arguments. That's cos 7 pi over 12 plus 2 pi over 3 plus I sine 7 pi over 12 plus 2 pi over 3. Let's start to tidy this up. That's going to give us 45. 2 pi over 3 is, what's that going to be in terms of 12 times by 4? So it's 8 pi. So 7 pi plus 8 pi then gives us 15 pi over 12. That gives us 45 cos 5 pi over 4 plus I sine 5 pi over 4. And then again, we're not actually in we're not in the range between minus pi and pi. So if you do 5 pi over 4, just very quickly over to this side. If you're going this way here, remember that would take you around the pi, so that's 5 pi over 4, so it's actually going to be around here. So it's minus 3 pi over 4 is really what we're going to be doing. 45 cos minus 3 pi over 4 plus I sine minus 3 pi over 4. And we end up then with that. Okay, and that's, we've changed that because the principal argument must be between minus pi and pi. All right. We're asked to write this in the form a plus ib, so we need to try and work. We've kind of worked out our argument and we've worked out then the side, so you kind of do it that way, but we're just going to muck around with this and see if we can change a little bit. That's the same as 45 cos 3 pi over 4. Why is that? Because cos of 30, for example, is the same as cos of minus 30. Cos of pi minus pi over 4 is the same. The minus can just come out of it whenever it's cos. If you think about the graph, for example, even, you know, the graph kind of goes like this. So anything over here is the same. There's a line of reflection in the y-axis. That's why then all the angles are the same. And then for sine, you can actually bring the minus sign out here. So it's minus sine 3 pi over 4. And we have that. Rewriting that then, 45 cos of 3 pi over 4, put that into your calculator, you get minus 1 over root 2. And then minus 1 over root 2i. Multiplying out your brackets. You get minus 45 all over root 2 minus 45 all over root 2i, and that's it then in the form that we need.